Hi, what is artificial intelligence? Well, that's a very interesting question and a very interesting topic, which has been discussed in mass and social media extensively over recent years. It's become one of those topics that used to be sort of somewhat science fiction, somewhat theoretical, and now has sort of come into focus of mainstream media, of let's say normal people, unlike engineers such as myself. But what is artificial intelligence? Well, that turns out to be a question which is somewhat difficult to answer. There have been both sort of social studies and also academic theoretical studies trying to define what we actually mean by artificial intelligence. And it turns out that isn't easy to do. One approach, however, which is kind of based on this famous Turing test, is to say that AI is software, that is computer software, operating inside a computer, hence a machine, which has some sort of traits that we typically associate with living things, like, let's say, humans. This sort of traits, it could be the ability to learn, the ability to think, or the ability to somehow reason about certain problems. Now, this definition is somewhat vague, of course, and it's more sort of philosophical than technical. And another way of looking at this problem of understanding what AI really is to consider this task of problem solving. Usually, when engineers do problem solving, we analyze the problem ourselves. We read up on the sort of surrounding contextual information which we need to understand what's going on, and then we figure out a solution, and we implement that solution in a computer program. In AI, however, we turn this whole scenario kind of on its head, and we say that we don't try to figure out necessarily the solution by ourselves, but instead we describe the problem in such a way that the computer can figure out the solution for us. So we define the problem instead of defining the solution. Now, it turns out that there is a fairly large range of both tools and methods which can be considered part of this AI umbrella or AI field. And there's also a bunch of different types of problems that can be solved with AI. One example would be navigation. If you want to travel from point A to point B inside some map, or naturally you travel in the real world, but you do have a map which tells you how to get there from A to B. In such case, you have a bunch of choices. You can go from A to B in many different ways, but all of those ways are not equally good. So you need to have some sort of way of deciding which of those choices is the best one. And this is kind of a simple but still typical AI problem, where you have some sort of information that you can use to find a solution which is optimal to your problem. In this case, that would be the map and the associated metadata, like distances of roads and traffic information, maybe contextual information, which helps you to figure out an optimal route. But you also need some sort of a goal description. You have to define what optimal travel route means in your particular case. Is it traveling from A to B as fast as possible? Is it driving the fewest amount of kilometers, using the least amount of gas? Would you like to place sort of weight on avoiding toll stations or ferries, if that's relevant to your particular journey? All of those things goes into defining the problem. And the solution to the problem is, in this case, a relatively simple search algorithm. But that could be considered a form of AI, because it requires a certain deductive reasoning to figure out what really is the optimal route to travel. And indeed, this mapping and route planning problems is an important class of problems within the AI field. Another topic which we have to talk about in the context of AI is this topic of machine learning. Now, in many cases, people confuse these two terms and think that they are sort of the same thing, which is kind of understandable because machine learning has become such a popular field that a lot of the AI work that gets sort of the mainstream media's attention has to do with machine learning. But actually, machine learning is a subset of AI. We said initially that AI is software which has sort of traits we associate with higher level biological beings, intelligent life. And learning is, of course, one of those traits. But there are also other types of AI which doesn't really rely on learning. So in other words, machine learning is a subset of AI. All of machine learning belongs to the field of AI, but there are also other types of AI which is not machine learning. And machine learning specifically then is software that has the ability to learn from data. It's a specific trait we associate with intelligence. But why is it that we call machine learning specifically for learning? Well, this word learning means, of course, to acquire knowledge. When we learn, that's what we do. We acquire knowledge either from other people, from a book, or basically just from experience, from our own observations. And it's interesting when we talk about machine learning that very often our focus is on the fact that this is algorithms, computer software doing something, which is natural because in the AI world, that's the exotic part. If it was just intelligence, it would be just normal world. But the fact that it's computers being intelligent or computers learning, it's natural that this is where we sort of place our attention. But I like to point out when I talk about machine learning that we call this learning for a reason. And the reason is that learning, as I said, by definition means to acquire knowledge, which is actually exactly what we do with machine learning tools. We have some kind of a system which we would like to learn something about. So we collect a bunch of measurements, which becomes our data set. And on those data, we apply machine learning. And the product of this process is a model, a mathematical construct with its parameters being calibrated to fit the particular system of interest. And this model can be thought of as representation of the knowledge of the underlying system. And this is not as exotic as it sounds when we as engineers or physicists develop physical models of systems in general. Like we could take some sort of a process plant or physical system and we could develop a mathematical model describing our own intuition or our own understanding of how that system works. That's also a mathematical model, which is a representation of our knowledge of that system. The only difference here is that the model structure is more sort of a general mathematical construct with a large number of parameters. And through calibrating those parameters to a particular system, that model also becomes a representation of the underlying system, of knowledge of the underlying system. Naturally, there is nothing magic in this process. Machine learning is simply a clever practical engineering tool. There is no magic involved, obviously. And there are certain requirements that we have to fulfill to get machine learning to really work. And two of those requirements, which is perhaps somewhat obvious, but still something that I find in many cases people do wrong when they try to use machine learning. And the first thing is that we really need to know sort of what we are trying to learn. We have to be able to define some sort of mathematical function which just describes how well we have learned what we want to learn. And also we have to be sure that the data that we are interested in is actually contains the knowledge that we are trying to extract. We cannot extract knowledge which is not in the data to begin with. And that second part requires careful design of measurements, experiments, and so on to really ensure that we have good quality data for the particular problem that we are trying to solve with machine learning. I mentioned initially that one of the demarcations of AI is that we sort of turn this problem on its head by saying that we wish to define the problem and then use some sort of a general approach to solve that using a computer. And one way to highlight this approach is to compare with the classical programming paradigm, where we develop a model. It doesn't necessarily have to be a mechanistic sort of mathematical model, but it could be a bunch of if statements, so a piece of software code could in this case serve as a model, but some sort of representation of our own understanding of how the program is supposed to produce a particular result given a certain input data. That of course requires us to be able to build that model in the first place, whereas the machine learning, or indeed the AI paradigm, tries to flip this upside down and say that we will feed the algorithm our data and the result we expect to see, and then we will let the computer figure out what the model should be in order to provide those results. And then in the second phase, of course, we can use that model in this sort of classical context where we apply new data with our calibrated machine learned model, and then we can make new predictions, new results. So why then has machine learning become so popular? Well, it turns out that there are quite a lot of cases where describing what we want to know is much easier than to figure it out ourselves. And the sort of trivial case of this, or maybe not trivial because the problem itself is not that trivial, but at least somewhat understandable example of this sort of approach of defining the problem instead of the solution is this task of building an algorithm which can, by use of a camera, tell the difference between cats and dogs. Obviously, this is something which is very simple for humans to do. Even small children are able to figure out, after 1 or 2 years, difference between cats and dogs. But it's turned out to be really, really difficult for a human programmer to design a model or a program which teaches a computer how to separate dogs and cats in pictures. But it's very easy, of course, for us to do that. So we can take a bunch of images of animals and we can sort the cats from the dogs in 2 different folders. We can then explain to the computer that this is what a cat looks like and these are dogs. And then the computer can learn the model, learn the knowledge that's sort of inherent in the fact that we separated those 2 types of animals from each other. And then the computer can figure out what model it needs to use in order to do the same. And that's pretty much what is the key to machine learning, that we can, by categorizing and labeling data, we can sort of tell the computer the necessary information it needs to learn the difference between these 2 different classes of animals. So a somewhat philosophical question maybe, which I think is interesting to discuss, namely because it's very often brought up in media and discussions about AI, which is, can these fields of machine learning, specifically in AI in more general terms, really make computers intelligent? Well, I believe that, or it's my experience that all data-driven methods are based on sort of 3 concepts. We have some sort of information structure, a model structure, sort of a general mathematical construct with lots of parameters, or at least some form of description of the problem that we wish to solve, or the solution that we wish to obtain actually. And then we have some kind of goal description, something which can quantify how good a particular version of this information structure happens to be. And the third one is we have some kind of algorithm or software tool which is able to guess or adjust our information structure in order to make it better. And then we can put these 3 things together and we have machine learning or AI basically. And I think that it is reasonable to argue that intelligent behavior in AI largely comes from the design of these 3 concepts. That AI, artificial intelligence, I like to say it's more artificial than intelligent. And by that I mean that the intelligence that appears to come from AI methods or machine learning methods actually comes from how we build up these three different parts of the algorithm. So if we have a cleverly designed information structure, a well-defined goal description, and a well-engineered optimization algorithm, then we can put those three things together and we can build an overall algorithm, an AI algorithm, which can exhibit intelligence. It can appear to be intelligent, but doesn't mean that it actually is intelligent. It's just artificially intelligent. And therefore we could say that this intelligent behavior in AI, in software, is a result of intelligent engineering. It's our own intelligence built into these three constructs, which together form the problem description that we are trying to solve. That's what makes AI smart, makes it intelligent. And to further highlight that point, it's interesting to look at what sort of problems are difficult or easy for an AI to solve. And the first type of problems which has been very popular in the AI research field ever since the beginning of the AI field, I would say, is this playing of games. And I think probably the first globally interesting event in the AI field was the defeat of Garry Kasparov in 1996 by IBM's Deep Blue chess computer. It was really the first time where something that was man-made was able to best a human in something that we consider an intellectual exercise, namely playing chess. And this evolution of chess computers, it didn't of course stop in 1996. It was developed continuously all up until present time. Now we have things like Google's AlphaZero engine, which learned to play chess by playing against itself, and has evolved even further from there. And now we are at a point where the best chess computers in the world are so good that even the best humans have zero chance of defeating them. In fact, they are so good that they are used by the elite chess players in the world as tutors. They use them as trainers, and they play against this software in order to learn new strategies. And this has been evident in recent World Championship chess matches, where suddenly these elite human players start to play new positions on the board, which hasn't really been part of the classic sort of chess strategy literature. And some of that is due to playing against machine learning based computer algorithms, which are able to come up with sort of new ideas, new constructive ideas on how to play chess, which positions in chess is good for a human player also. Another sort of large class of problems is this idea of finding patterns in complex data. So we have a very large data set, much too large for any human to sort of absorb and analyze and understand. But for a computer, finding patterns in data is relatively straightforward. If we are able to define for the computer sort of what patterns we are looking for and in some way how these variables in the data is related to each other, then the computer can help us to find the relations between variables and sort of decipher the complexity of the data. This is also a kind of task which is relatively easy for a computer to do, but it may require a long time. It may be computationally intensive, so it can take hours, days, weeks, even months to solve very difficult, complex AI or machine learning mapping problems. But that doesn't mean it's necessarily difficult or hard for the computer. It just takes a long time. So what about something like playing football, for example? We would assume, kind of, if we didn't know better, that if a computer can learn to play chess, it should also be able to learn to play football, which we generally consider to be, at least most of us would consider it to be intellectually simpler than playing chess. And no offense to football players, of course. I'm sure it's very challenging to play football as well. Certainly I cannot do that. But I think in terms of intellectual level, most people would agree that chess is harder than football. But for computers, it turns out to be ridiculously difficult to play football, because for a computer to learn how to move its arms and legs and run around a football field and kick a ball into a goal is extremely hard. There is a lot of factors involved. There is sort of the physics of the android or the robotic body that's used to move around the field. It's the physics of the ball, wind resistance, bouncing of balls on grass, for example. A lot of different parameters that goes into this game of football, which makes it really, really difficult, really complex for a computer to understand. And what about walking, jumping, or doing a backflip? It's of course similar to playing football. It requires a lot of control over some sort of body, of course an artificial one in the case of robots. And that is ridiculously hard for a computer to figure out or learn how to do that. And there's only very few robots in the whole world who are able to walk in a sort of more or less adequate sense or adequate way in the sense that we would consider walking. Of course, you can easily build a walking robot by having 6 legs, then it's statically stable. That's just 2 chairs moving on top of each other. Or you can have very large feet so that you're always sort of stable. Then it's simple. But that's really not walking, that's just sort of sliding around. But actual walking, where you have to maintain balance, is super difficult for a computer to figure out how to do. And the last thing, what about driving a car? Well, it turns out to be also very difficult, and perhaps more difficult than people in the field expected. There were some breakthroughs in 2012 when this Stanley, built by Stanford University, finally made it through this DARPA Grand Challenge, 212 kilometers race through the desert without any human intervention. And that was a real breakthrough for self-driving cars. And there are, of course, now self-driving cars running around in traffic, usually very slowly, because it can be dangerous to go fast if they make a mistake. But it's interesting to observe that Tesla, which is one of the forerunners of this race, at least in terms of commercially available self-driving cars, they seem to be always ready in 2 years. They were saying that they will be done in 2 years when I started talking about this back in 2017, 2018. And they're still saying they're about 2 years away from full self-driving capability. So it seems like driving car is also one of those problems which is really difficult for a computer to figure out to do. And that's perhaps not surprising if you think about the fact that everything you have to deal with while driving, it's not just the traffic rules and understanding all the signs, but you have to deal with the physics of the car and the road. You have to deal with obstacles and with interactions with the people and other cars. And some of that is also requires some social intelligence. You have to understand human behavior to be a good and safe car driver. And that's very difficult for a computer to understand. Complex problem. So what does these things have in common? What is the commonalities between the easy things and the hard things? Well, in my mind, it seems to me that the things which is easy for us to get a computer to do is the things where we can easily describe the problem. The problems that can be easily solved by AI are the problems that has some sort of rules which we can easily describe in a language that a computer can understand. Chess, for example, is actually a very simple rule set. It's only 64 different squares on the board. It's of course 2 times 8 pieces, and they have fixed patterns of movement. Of course, it's still a lot of different positions that these chess pieces can take on. In fact, it's something like 10 to the 123rd power of different possible chess games that you can play. And a lot of those games have never been played, naturally, because in the whole history of the human race, there's never been played as many as 10 to the 123rd power of chess games. But still, in terms of a rule set, it's still fairly easy for a computer to manage that. Compared to driving a car or playing football, the possibilities and the different combinations and permutations of what can happen is infinitely larger. It's impossible to describe that in any adequate sense, at least for now. very difficult to define the problem of playing football for a computer. At least if you consider the actual act of playing football. An example here could also be to consider if you simplify the game of football to being sort of a strategy game where all the players do play perfectly all the time and you take all the physics out of it, so you're just interested in football strategy, then it would be easy to define for a computer and therefore also easy to solve. But the key thing here is understanding that what makes AI intelligent is our ability to describe the problem in some way that allows the AI to do intelligent things. And therefore the solvable problems have that in common, that they lend themselves to being described by rules which the computer can deal with. So to summarize a bit, the definition of AI, or one definition of AI, is software which has some sort of human trait, some sort of property or ability which we think of as human, or at least belonging to intelligent life forms. Could be learning, thinking, deductive reasoning, along those lines. And this is also evident by this Turing test, which is one way of measuring the quality of AI by placing the AI computer inside a locked room and only interacting with it from a sort of a text-based terminal. And if this AI is able to interact with a human through this text-based terminal in such a way that an external human observer, which doesn't know if he or she is communicating with a computer or a human, cannot tell the difference, then we consider this to be sort of a human-level AI. That's basically what the Turing test says. And it highlights this definition of AI, that it has to do with what an external observer would consider intelligent behavior. I think it's important to consider this intelligent behavior of AI as an emergent property, and it comes from this design of problem descriptions. The more clever problem descriptions we can invent, the more clever AI will be. And that goes to information structures. How do we construct these generic mathematical model constructs, which is used by AI to learn or to calculate or to reason? And also, how do we define the goals of what we are trying to achieve with these algorithms? And intelligent behavior in this context of AI is simply the result of intelligent engineering. But of course, AI and machine learning, if it's done right, and by that I mean with the proper care of how we do data collection and experimental design, how we define our problems, and how we choose what model structures and methods to use, is clearly a very powerful engineering tool. It's a practical engineering discipline. There's nothing magic involved, obviously. It requires a lot of experience and hands-on sort of trial and error in order to learn and get an intuition for what is the right and the wrong things to do when you are designing an AI or ML approach to a particular problem.